All right, Calculus 12 students, here is the video on lesson number 4 in chapter 4. And for lesson number 4, we're going to be taking a look at derivatives of inverse trig functions. Now, in the previous classes, we did spend some time graphing the inverse of trig functions. So you may recall that I did ask you to graph functions like the sine, cos, and tan. So I've asked you to graph their normal graphs, and we also had an opportunity to graph their inverses. So if you have the graph of the inverse of sine x, so this is the inverse of sine x, you may recall that the graph may have looked like something like this. And if you had the graph of the inverse of cos, the graph, I believe, looked something similar to that. And for tan x, this is the graph that had the horizontal asymptotes, and your graph was something like that. Okay, so these are the kind of graphs that we did graph in the previous lesson, and for today's class, we're going to be looking at how can we find the derivatives of these graphs so that we can find the derivative and the slope at any given point. So if I want to find the slope right here and draw maybe a tangent line, I want to be able to find that slope, and therefore I need to understand how to find the derivative of these inverse functions. Okay, so if you look at this table here, this big table right here, this table gives you the derivative of all the inverse functions, and the good thing is you don't have to memorize this. This will be given to you, but you just need to understand how to use this table here. Now, for the questions in this lesson, sometimes you might see the inverse of like sine. Sometimes it may be written like that. Other times it may be written like arc sine. All right, so arc sine and the sine to the power minus 1 of x, they all mean the same thing. So this one right here, you could see it as cos minus 1x or arc cos x. And for tan to the power minus 1x, you could see it like that, or it may be written as arc tan x. Okay, so that's the first thing I wanted to mention is you need to be familiar with the different kinds of notation when we're dealing with inverse trig functions. Now, for the first part of the video, I want to show you how we actually get to the derivative of these inverse trig functions. So I will show you how to find. I'm going to show you how to derive this derivative here, and I will also go over how to derive the derivative of secant. The inverse of secant x. So once I show you how to derive those, then we're going to actually apply this table here to several problems. Okay, so let's get started with the lesson now. So the first part of the lesson is I want to show you the proof of finding the derivative of the inverse of sine x, so that we get 1 divided by the square root of 1 minus x squared. So I'm just going to zoom in here and pull this up. Okay, so before I start this proof, I just want to go over some basic trig identities and some basic trig ratios. So if you have something like sine theta, and if you're dealing with a right angle triangle, the ratio for sine theta is going to be the opposite divided by the hypotenuse. Okay, so that's something that I will be using for this proof here. And also, when you were solving trig questions back in like grade 9 or grade 10, you may have come across problems such as sine theta equals to I don't know, 0.654, and your job was how do you find this angle such that sine of that angle will give you 0.654. And when this problem is introduced at the grade 10 level, we generally ask students to go to their calculator, and in order to solve this problem, students would go to their calculator and they would do this sine to the power of minus 1, and they would do sine to the power of this minus 1 here, and just go right to your calculator. And this part right here, I mean, that pretty much undoes the sine, and you'd just be given the angle there, and you'd be given like sine of minus 1 of 0.654. Okay, so this little this part right here in blue is something that I'll be using in my first proof. Is if I want to get rid of the sine to the power of minus 1, I need to multiply by the sine, or if I want to get rid of the sine, then I need to multiply by this sine to the power of minus 1. Okay, so let's get started with the proof now. Delete all that. Okay, so here we go. My very first step is I'm just going to let the variable y equal to the inverse of sine x. Okay, so I'm just going to drag that in over here and let y equal to sine the power minus 1x. All right, so the next step that I'm going to do here is I want to get x by itself. So this variable right here, I want to get that variable by itself. So in order to do that, I need to get rid of this sine to the power minus 1. So in order to do that, I need to multiply both sides of my equation by just sin. So I'll multiply this, the left-hand side by sin. So if I multiply both sides by sine, I get sine y, and that's going to equal to just the variable x. Okay, so you'll notice that this part will just cancel off now. Okay, so sine y equals to x. Now, if I look at this expression right here, that's very similar to this expression right there, where I have sine theta equals to opposite over hypotenuse. So what I can do right here is I can just make this x equal to the ratio of sine, which is going to be opposite over the hypotenuse. Okay, and that means my hypotenuse here is going to be 1. Okay, and then the next thing I'm going to do now is I'm going to draw a triangle, and I'm going to try to put this ratio in here. So here's a right angle triangle. And let's just pretend that this y is this angle right here. Sorry, not theta, but let's just call this y. And that means this will be my opposite, and this will be my hypotenuse. Okay, so in this case, my opposite is going to be x. So that's this guy right there. And my hypotenuse here will just be 1. Okay, and hopefully you can see that that 1 is this guy right there. Okay, so I'm just going to delete all this now. Okay, and then the question is, you need to find the adjacent side here, and in order to find the adjacent side, you would just use the Pythagorean Theorem. So that's going to be, a squared plus b squared equals to c squared. So this would be like question mark squared plus x squared equals to 1 squared. And after you do all the math here, the question mark is going to be the square root of 1 minus x squared. Okay, so let me just kind of delete this here, delete that there, and I get this square root of 1 minus x squared. Now that you've seen this triangle being constructed here, let's just go back to our derivative of sine. Let's go back to the derivative of the inverse of sine, and this part right here. I mean, this 1 minus x squared all square root. I mean, that's looking very similar to. Sorry, if I drag that down here, it's looking very similar to the adjacent side right there. Okay, so when we're doing these trig proofs for inverse functions, a lot of it is coming from like a right angle triangle. Okay, so let's continue now. So I have sine. I have this expression right here of sine y equals to x. All right, so same thing. Now, in order to continue finding the derivative now, all we need to do is let's just take the derivative now of this expression here. So let's take the derivative here, and let me just kind of delete this, and let's just take the derivative of that so that we can finish the proof here. Okay, so before we do this, this sine y and this x, like sine y equals to x, even though it looks different, but since I've multiplied both sides by sin at the beginning, this expression right here is very similar to, is actually the same thing as of the inverse. So taking the derivative of the inverse would make sense in this case. Okay, so now the question is, what's the derivative of sine y? Okay, now going back to some previous notes, the derivative of just a regular sine x, that's going to be cos x. So if I want to take the derivative of sine y, I mean, that's going to be the same thing as cos y, but then I need to apply the chain rule and take the derivative of y, which is going to be dy by dx. Okay, so this expression right here is that guy right there. Okay, so this is going to be cos y dy by dx, and I'm just going to go ahead and erase this now. And the next derivative here, I mean, what's the derivative of x? Well, that's going to be 1. Okay, And then all we do next is we just need to isolate for the dy by dx, because that's the notation for derivative. So dy by dx will equal to 1 divided by cos y. Okay. Now we're almost done here. Now in order to kind of simplify this problem here, you have to ask yourself, what is cos y? Well, go back to your triangle. Alright, so here's my y. Cos y is your adjacent divided by your hypotenuse. Alright, so that's just a trig ratio. So using that trig ratio here, your adjacent over your hypotenuse, what's my adjacent? Well, my adjacent is the square root of 1 minus x squared, and my hypotenuse is going to be 1, and this will simplify to be 1 minus x squared. So cos y is the square root of 1 minus x squared. Alright, so all we have to do now is we just need to insert this back into the cos y, and we get 1 divided by the square root of 1 minus x squared, and that is the proof of the inverse of sine x. Okay, great. So now that you've seen that proof, let's go ahead and do another proof here. Let me just zoom in here. And one question that students will ask me is that, will you test us on how to derive the derivatives for these inverse functions? And just to be honest with you, I probably won't ask you to derive the derivatives of inverse functions, unless you're, of course, someone that needs to do more work in the course, like Reese. So the only student that's really responsible for knowing these proofs from scratch would be Reese, but everyone else, I'm more interested in whether you can actually use the derivatives for these inverse problems. Okay, so let's move on with the proof of secant minus 1 of the x. And make sure you fill in your notes, because I will do a note check when I see you guys next time. So let's go ahead and do this proof here. So before I start this proof here, for those students who didn't take the pre-calc 12 class, secant x is actually equivalent to 1 over cos x. Okay, so that is a trig identity. So secant x is defined as the reciprocal of cos x. And the reason why that's important is because if I have cos x, the trig ratio for cos x when you're dealing with right angle triangles is that cos x is your adjacent over your hypotenuse. All right, so if you remember your SOHCAHTOA, the cos ratio is your adjacent over your hypotenuse. So if I'm dealing with secant x is basically the reciprocal of cos x. So the reciprocal is 1 over cos x, and if I delete cos x here and replace it with your adjacent over your hypotenuse, and if you do a little bit of math here, I mean, this is the same thing as your hypotenuse over your adjacent. Okay, so this part right here will be important for the next proof. Okay, and one of the reasons why I want to do a proof of the secant inverse function is because the secant inverse function has this absolute value here, and I want to explain why that's the case. Okay, so make sure we make sure we're okay with that ratio right there, and then now we can start the proof. And I need a little bit more space, so I'm just going to delete all this. Okay, so let's start the proof off with a let statement. So let's just let the variable y equal to the inverse of secant x. Okay, so this part right here is that part right there. And what I want to do now is I want to isolate for this x variable. Okay, so in order to isolate for that x variable, I need to get rid of this secant to the power minus 1. So that means I'm going to multiply both sides of my equation by just regular secant. So multiply that side by secant. If I do that, I will get secant y equals to just the letter x. Okay, so let me just delete all this now. So basically, I multiply both sides of this original let statement by secant to the power minus 1. So these two lines right here, line 1 and line 2, they are equivalent, okay? But line 2 is much easier to work with because I can take the derivative of that, okay? So one of the reasons why I multiply both sides of the equation by just regular secant is because I want to get back to a basic trig function where I can actually take the derivative of this trig function. Okay, so just remember the derivative of secant x. All right, you can find this in your reference sheet. The derivative of secant x is going to be secant x tan x. Okay, so eventually I want to use this derivative here to kind of finish off or get to the next step in the problem here, or the next step in the proof. Okay, now before I actually get to taking derivatives, I want to kind of simplify line number 2 here. So this is line number 2. Remember, secant x is the same thing as your hypotenuse over your adjacent. Okay, so that means this ratio is the same thing as x divided by 1. Okay, and if I go ahead and construct a right angle triangle here, where that is my 90-degree angle there, and let's just call this y, and that's just corresponding to that guy right there. You know, this is my hypotenuse again, this is my adjacent side. If we go ahead and plug in those values here, we will get triangles. Our triangle will look like this: x, and my adjacent is 1. And if you use your Pythagorean Theorem again and find this side right here, and if you do the math there using your a squared plus b squared equals to c squared, this is going to be the square root of x squared minus 1. Okay, so there's my triangle there, and I'll be using this triangle to kind of finish off my problem. So let me just put this in a box for now, and I'll go back to this towards the end of the problem there. Okay, so going back to line number 2, I want to work with this expression right here. All right, and I want to find the derivative of that expression. So I want to go ahead and find my derivative of line number 2. So if I write the proper steps here and have the right notation here, this is the notation that I would use. I'm taking the derivative of the second line. And once again, the derivative of secant y is going to be secant y tan y. And because we're taking the derivative with respect to y, I do need to apply the chain rule. I mean, this part right here is the derivative of secant theta, or secant y, and then I need to apply the chain rule, and I need to find the derivative of just my general y here, and that's going to be your dy by dx. Okay, so if you're not familiar with taking the derivative of your trig functions, make sure you look at your reference sheets, because we will have a quiz on this in the upcoming week. Alright, and this part's easy. What's the derivative of x? That's just going to be plain simple 1. Okay, so whenever we take a derivative implicitly, we need to isolate for this dy by dx here. So let's go ahead and isolate for that term now. So dy by dx is going to equal to 1 divided by secant y times tan y. Okay, now in order to kind of finish off this proof here, I need to go back to my triangle, and let me just kind of zoom out now and go back up here. Okay, so in order to kind of take care of the denominator here, I need to go back to my triangle here, and let's just go ahead and find the ratios for secant y and tan y. Okay, so well, secant y, this part right here is basically this part right here highlighted in green. So I'm just going to highlight this part in green here. Secant y is just equal to x, and x is your hypotenuse, right? So if I go ahead and finish this off here, secant y is just going to be the letter x. It's just the hypotenuse. And then I want to find tan y. So I'm highlighting tan y here in green. So if I go back to my triangle here and find tan y is your opposite divided by your adjacent. So my opposite in this case is going to be the square root of x squared minus 1, and my adjacent is 1, and that's just going to be the square root of x squared minus 1. So I'm going to put my square root of x squared minus 1 down here, and that's going to be dy by dx. Now I'm almost done here, and the final thing I want to kind of explain here is that this x value that I'm highlighting in yellow right here, that is your hypotenuse. All right, and the hypotenuse for a triangle is always going to be positive. So in order to kind of illustrate that x will always be positive, it's just proper to write the absolute value sign in there, right? So the hypotenuse will always be positive, even if you're dealing with a unit circle, because both sides will always be squared. The hypotenuse will always be positive. Okay, so there it is. That concludes the proof for secant, the inverse of secant theta, or secant x. Sorry, the inverse of secant x. And now let's go on and do some problems with this. Alright, so let's get into the problems now for this section. So the very first question is, find the derivative of the following functions here. So f of x equals to arc sine of x divided by 2. Now the first thing I want to point out is this notation here of arc sine, and if you see something like that, you need to recognize that this is basically the same thing as sine of the inverse of x over 2. Okay, so just to be comfortable with the notation that's kind of given to you in the problems, you might be given arc sine, or you may be given the inverse sine, but they mean the same thing. And since this is kind of a new problem for us, I'm just going to go ahead and go to my reference sheet and write down the derivative of the inverse of sine x, which is going to be, hold on, what's that going to be here? Let me just flip my pages here. This is going to be 1 over the square root of 1 minus x squared. Okay, and hopefully you can recognize that this x squared term here, or that x value there, is actually corresponding to this part right there. Okay, so that's the part that you want to square. So if I go ahead and now take the derivative of this function here, I'm going to write my derivative notation here, which is f prime of x, and that's going to equal to 1, and that 1 is coming from, you know, this 1 over here on my derivative, all divided by the square root of 1 minus x squared, and my x squared term is x over 2, so this will be x divided by 2 all squared. Okay, so hopefully that matches up with this guy right there, and my x squared term is x over 2. And now I'm going to erase all this. You need to apply the chain rule here, because we have this x over 2 term there, so if we apply the chain rule now, the question is, what's the derivative of x over 2? And that's simply going to be 1/2. Okay, so I'm going to times that by 1/2. And hopefully that's okay, because if you see this, I mean, this is the same thing as y equals to 1 over 2x, you know, and this is right here is your slope, right? So y equals to mx plus b, and your b value would be 0, so that's the slope of x over 2 is simply going to be 1/2. And if we go ahead now and just simplify the problem here, I'm going to put this 2 right here on the denominator. So the final answer here would be the square root of 1 minus x squared divided by 4, and I'll put the 2 in front of there, and this 2 is just that 2 right there. Okay, so here it is. There's my final answer for the first problem. As you can see, doing the problems doesn't take a long time. You just need to apply the derivative rules and just simplify the problem. Okay, let's move on. Next question here is y equals to arc cos of x squared minus 9. Okay, so I'm going to highlight this arc cos here, because if you see something like that, that's the same thing as the inverse of cos. So this is x squared minus 9. Okay, so now that I see this expression like x squared minus 9, that's a good indicator that I will probably use the chain rule for this problem. And the derivative of the inverse of cos is -1 divided by the square root of 1 minus x squared. Okay, so let's use this rule right here, and let's go ahead and apply this to this problem here. Alright, let's take the derivative, so I need y prime. So now I'm taking the derivative of the inverse of cos, so that's going to be 1 divided by the square root of 1 minus. Okay, so the rules say I need to take my x term and square it, so this right here, I mean, that's my x term, right? And I need to square that, so that's going to be x squared minus 9 all squared. I apologize, it's not very neat there, so let me just rewrite this. This will be x squared minus 9 all squared. Let me just extend the line there. And then I need to apply the chain rule and take the derivative of x squared minus 9, and that's going to be 2x. Okay, and then right away we just simplify. So this is going to be, sorry, I forgot the minus sign here. Okay, so this minus sign corresponds with the minus sign right there. Okay, so the final answer is going to be negative 2x, all divided by the square root of 1 minus, and I'm going to put this all in brackets here because it's neater to put it all in a bracket there, and there it is. There's my final answer right there. Okay, let's move on to the next problem here. Y equals to arc secant 2x. So this is the same thing as y equals to x times secant inverse of 2x. Okay, and now that you see there's an x term there, that's a good indicator that you're probably going to have to use the product rule. And since you see the 2x here inside the theta position there, that's another good indicator that you need to apply the chain rule. Okay, so if you went to your reference sheet, the derivative of secant inverse, this is the proof that we just did in the previous page. This is the absolute value of x times the square root of x squared minus 1. Okay, so that's the derivative of the inverse of secant x. Let's go ahead and apply this to the problem here. But now if we use the product rule here, the product rule means that the product rule states that you need to take the derivative of like your first term times it by the second term plus the derivative of your second term times the original function, I guess. Okay, so I don't want to write out the product rule here, so let's just go ahead and apply it here. What's the derivative of x? Well, the derivative of x is going to be 1, so then you're left with secant to the power of minus 1 2x, and then the product rule says you need to add that to now the first term, which is going to be x, and then times it by the derivative of the second part, which is the inverse of secant 2x. The inverse of secant 2x. Okay, so in order to find the inverse now of this part right here in your question, you go ahead and use the rule for the derivative of the inverse of secant x, and that's going to be 1 divided by the absolute value of 2x times the square root of 2x all squared minus 1. And then I'm going to go ahead and I will simplify this. This is going to be secant to the power of minus 1 2x plus, well, there's not much you can simplify here. I'm just going to take this x term here, highlight in yellow, and put that all in the numerator there, all divided by the absolute value of 2x times the square root of 4x squared minus 1. And there it is. Here's your final answer there. Okay, let's move on to question number 4 now. Arc tan e to the x. Okay, so once again, this is the same thing as tan to the negative 1 of e to the x. Now, there's a few things I want to write down, from your reference sheet here. First of all, the derivative of the inverse of tan x. That's going to be 1 divided by 1 plus x squared. And the derivative of e to the x. Now this was also coming from from the previous lesson, from one of the in-class assignments, in a way where I asked you to graph e to the x as well as its derivatives points, and as well as the derivative points for e to the x. And a lot of students came to the conclusion that it was the same thing as e to the x. So the derivative of e to the x is just e to the x. Okay, and you can go back to your in-class assignment or the class notes to kind of confirm that through the graphs. Okay, so now that we know those two identities there, let's go ahead and find the derivative here. So this is going to be y prime equals to 1 over 1 plus bracket e to the x squared times the derivative of e to the x applying the chain rule, and that's going to be e to the x. So this here simplified is going to be e to the x divided by 1 plus e to the 2x. All right, so that's your final answer once you've simplified everything. This 2x right here, highlighted in yellow, that's just simply multiplying the exponents right there. Okay, so this isn't too bad, right? So if I go back, if you're not sure how I did the substitution step, if I have e to the x there, I mean, I'm just plugging that in over here and squaring it, right? Okay, so hopefully that's not too bad, and I'm going to move on to the next problem now. Okay, so for the next few problems here, I'm just going to go ahead and just solve the problems now. I'm not going to write down what the derivative is or for the inverse here. So this is going to be -1 divided by the square root of 1 minus bracket 1 minus 3x, close the bracket, squared, and then you take the derivative of the inside part, and that's going to be -3. I can then simplify the problem, and that's going to be 3. So if I take this -1 and times it by -3, that's going to be positive 3, all divided by 1 minus bracket 1 minus 3x, all squared. Okay. All right. Yeah, so go ahead. I believe like questions 5 and 6, you know, they're not too bad. I'm just kind of using the rule for the inverse. I'm using the rule for the derivative of cos x, and I'm just inserting that. Sorry, I'm using the rule for the inverse of cos x, the derivative of that, and I'm just kind of plugging that into the formula there. Okay, and the last one here, I will go back to my reference sheet and find the derivative of the inverse of cosecant x, and that's going to be that's going to equal to -1 over the absolute value of x times the square root of x squared minus 1. And let me just kind of confirm if that's correct. Yeah, that's correct. So let's go ahead and now take the derivative now. So this is y prime equals to -1 divided by the absolute value of x. Okay, so the absolute value of x here, what is x? Well, this guy corresponds to that, so that's going to be the absolute value of x squared times the square root of, okay, so it's going to be x squared again minus 1, and then I need to apply the chain rule here, and if I want to find the derivative of x squared, that's going to be 2x, and then all I have to do now is just clean this up, so this will be -2x, all divided by the absolute value of x squared times the square root of, well, this will be x to the power 4 minus 1, and once again, this 4 simply comes from multiplying the exponents together. That's just a general exponent rule from your Math 9 class, and there it is. There is the final answer for that problem. Okay, let's roll on here. Okay, so question number 7, find the derivative of f of x equals the inverse of sine x of x cubed. So the derivative here would be f prime of x equals to 1 divided by the square root of 1 minus x squared, and well, this is my x term now, so that's going to be x cubed all squared times the derivative of x cubed, which is going to be 3x squared, and that's going to be 3x squared all divided by the square root of 1 minus x to the power of 6. And once again, this 6 is simply multiplying your exponents. Okay, next problem. Arc cot. Okay, this is an interesting problem here. I have arc cot of cosecant square root of x. Let me rewrite this as y equals to, this part right here is the same thing as cot minus 1 bracket cosecant bracket square root of x, close bracket, close bracket. Okay, so you know, this question right here isn't a product rule, because if you look at this cot here, I mean, that's very similar to like just cot of -1 of x, and this x term is kind of like this whole expression right there. So this is not a product rule question. It's actually an extended chain rule question. Okay. So this problem is, you probably have to use a chain rule 2 times for this question here. Okay, so let's go ahead and before I do this problem here, let me just write the derivative rule for cot x here, for the inverse of cot x. So the inverse of cot x is going to be d by dx of the inverse of cot x. That's going to be -1 over 1 plus x squared. Okay, so now that we know that fact, let's go ahead and apply this. So this will be y prime equals to, okay, so I gotta take the derivative of coat, the inverse of coat, so that's gonna be -1 divided by 1 plus, okay, so if I go back to my rule here, my rule says I need to take my x term and square it, and you need to recognize that my x term is all of this part right here, underlined in green, all that's being squared. So this is gonna be cosecant root x, all of it squared. Let me just extend the lines here. And then I need to take the derivative of the inside, which is actually this part right here again. So the derivative of cosecant, root x, going back to your reference sheet, so let me just kind of write the derivative of cosecant x. That's going to be negative coat, sorry, not negative coat, okay, so that's going to be negative cosecant x times cot x. Okay, so this is coming from your reference sheet again, and now I need to apply that to this part right here. So if I apply that, that's going to be bracket negative cosecant root x times cot root x. And now that I've taken that derivative here, let me just erase all this. And then I need to take the derivative of root x, and that's going to be 1 over 2 root x. Okay. And then if I go ahead and simplify this problem now, it's going to be y prime equals to, well, on the numerator here I have a minus sign at the beginning, and I also have a minus sign there, so that's going to be cosecant root x times cot root x, all divided by 2. And this 2, where is this coming from? That's just coming from this 2 right there. And then bracket 1 plus. Now this part here that I'm highlighting in blue, you may write it like as it is, or another way that you might see this written as is cosecant squared root x. So that's notation that we can use to kind of like simplify a trig function being squared. And then I'll multiply that by actually I'll put the root x over here as well. Sorry, I'm going to delete this at the beginning here and just put 2 root x. And I apologize for that. That 2 root x is simply going to be all of that part right there. So, and there you go. That's how you would simplify that problem. Okay. Now the good news is I've decided that I'm not going to do the last problem here because the reality is, so the last question is your typical find the equation of the tangent line to some function, and my function in this case is an inverse function here. When we do these kind of problems, it's the usual y minus y1 equals to m on to x minus x1, and this point right here, this x1 is this term right here. The problem for this question, in my opinion, is finding this y1 value here. And how do you find that y1 value? Well, you got to take your 2 over 3 and plug it back into your original function. Now, if you haven't taken the pre-calc 12 course, it's going to be very difficult because you do need to construct a triangle and you need to do some different ratios here. And I've decided that I'm not going to do this problem because for this kind of problem, you do need to have a better understanding of the concepts taught in pre-calc 12. So I've decided that I'm not going to test this kind of a question for this year. So we can stop the video right here. And I'm going to have one more video about a few other proofs, so stay tuned for the second video, and please watch that. And then during class time, we're just going to work on problems because that will be a little more productive for the final few lessons for this chapter. All right, we'll see you next time.